Sorry.
Listen.
If you don't know what it is, essentially here's the definition. It is applicable for every single level. The probability of an event occurring, that's what this notation means, is defined as the number of favorable outcomes, or let's just say number of ways E can occur, all divided by the total number of outcomes. First example. Okay, this is for every single level. You should know how to do this. If I roll two dice, I believe that's the plural, what is the probability of rolling a double? Double meaning what, for those of you that are more experienced? Two of the same number. Okay? We haven't talked about fundamental counting principle yet, but essentially, if you roll two dice, there are going to be 1, 2, 3, 4, 5, 6. How many possible outcomes?
36.
36. First die can be 1, and then the second die can be anything from 1 through 6. Similarly, on down, all the way from 1 through 6. Okay? I don't have to keep writing this, do I? You guys see what's going on? So where are the doubles?
On that one line.
1, 1, 2, 2. Where's the next one? 3, 3, 4, 4, 5, 5, and 6, 6. So how many ways can we succeed here in rolling a double?
6.
6 out of how many? 36. So answer 1/6. Okay? Questions? Obviously, you don't want to be writing out every single scenario or every single outcome, because sometimes there are millions of them. Okay, so one thing you need to get really good at is counting. Here are a few basics. Okay? If event 1 can occur in, let's say, m ways, and event 2 can occur in n ways, then event 1 and 2 can occur in, those of you that have been here, how many ways? M times n ways. This is what we call the fundamental counting principle. Okay? Simply saying that you just multiply your possibilities. So if I were getting dressed in the morning and I only have 4 pairs of jeans to pick from, and I have 7 t-shirts that I wear Monday through Sunday, and I want to switch it up and I don't know what I'm going to wear, how many outfits could I make? For those of you that were listening. 28. 4 jeans, 7 t-shirts, 28 possibilities. Okay? You could also do a tree diagram. If you don't see how that works, so we can call jeans J, so J1, J2, J3, J4, and then if I pick my first pair of jeans, for each pair of jeans there's going to be, what did I say? 7 possible t-shirts. 1, t-shirt 1, and so on, all the way down to t-shirt 7. So for each group of jeans there are 7 of them, therefore 4 times 7, which is 28. Okay, you don't have to do a tree diagram every time. As long as you remember that you multiply, then you are good to go. Okay? Let's see. Factorial is something that might be new for some of you. What does that look like? An exclamation point. Okay? It does not mean that we are really excited when we write down 5.
120.
Yes, how do we get 120? Okay, the factorial notation simply means that you multiply every integer, or every positive integer from 1 through 5. So 5, 4, 3, 2, 1, multiply it out, you get 120. Okay? If you have your calculators, I will show you where this button is, so take them out. Because a lot of times you don't actually want to compute by hand if the calculator will do it for you. Okay? So for those of you that have your calculators, if you press the math button and then go over to PRB, I think it's the first option.
Fourth.
I think it's the 4th option. Number 4. Okay, so if you wanted to compute 5 factorial on the calculator, you type in 5 first, go to math, go to probability, select the exclamation point, and you get 120. Okay, questions on where to go or how this works? Okay. One other thing that I'll add in the factorial section is this. N objects can be arranged in n factorial ways. So if I chose 10 of you to be 10 random objects, we could line you up in lots of different ways, lots of different arrangements. So for example, 10 people, if we lined them up, how many orders can we line them up in? How do we get that? 10 factorial, and what is it? 800?
Yeah.
Thank you, sir. Okay, so pretty easy stuff. Okay, if you don't like that, I could also explain it in this manner. If I have 10 people and I'm trying to pick who is going to be first in line, second in line, third in line, and all the way down to 10th in line, you can think of it this way. Just write out, first, second, third, fourth, put 10 little empty spaces there, and just think about the number of choices. So if I haven't chosen anyone to be first, how many people could I possibly pick to go first? 10. And then once I've assigned someone to be first, how many choices do I have for the second person? 9. This is just the fundamental counting principle, and I think you guys see, oh, wasn't that, yeah, that's the same as 10 factorial, right? 10, 9, 8, all the way down to 1. Does that make sense? Okay. With counting and with factorials, and keep your calculators handy because you need to know where these are as well, we have permutations and combinations. Permutations, combinations. Okay, think of permutations. Actually, that example we just did is perfect. It's arrangements or orders. Think of combinations as groups. In other words, for permutations, order is very important. Okay? If I have 10 people and I want to line them up in several different ways, we already know that there's over 3 million ways in which to do so. However, if I only have 10 people and the question is, And how many ways could I pick 10 people in a group of 10 to do something? What should the answer be? 1. Because if there's 10 people and I'm picking all 10 of them, there's only one group of 10 out of that. Okay, so that's the difference between a permutation and a combination. Here's how they are computed. Here's the notation. For a permutation, you do NPK. N represents the total number of items. K is the amount being selected.
You can sit there. It's in the camera.
And here's the formula for it. You do n factorial over n minus k factorial. Okay? And I'll do an example of each in just a second, both by hand and with the calculator, so you can see that they're pretty easy to calculate. Combinations, the notation is very similar. It's NCK. You know what I just realized? Your calculator uses R's, doesn't it?
Yeah.
Let me keep things consistent. Combinations is just n factorial divided by the same n minus, so this should be an R now. Okay, so it'll be divided by the same n minus R factorial, but now you also have to divide out chances for repeating those items, so we throw in the extra R factorial. Okay? So that's the definition for a permutation. This is the definition for how to count number of combinations. Okay, so here's an example that will illustrate both. I'll do it by hand, and then I want you guys to quickly do it on the calculator so that you can see how to work with that. Okay, so for example, let's say somebody has 8 books, 8 different books in their book bag. In how many ways, let's say orders, in how many orders can, let's say, 5 books be taken out? So if I have 8 books sitting in my book bag, and I just randomly take out 5 books, and how many different orders would there be for that? This is clearly a what kind of problem? Permutation, good. So by hand, the total is n, so that'd be 8 factorial, and then we divide by what? N minus r, so 3 factorial. So this is the formula for n, choose r, so, or not choose, n, pr. Okay, so this is what it would look like. So how does this look by hand? 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. This is the last time I'm ever going to write all the numbers out. What's 3 factorial? And 3 all the way to 1 cancel. So whatever 8 times 7 times 6 times 5 times 4 is the answer. What is it? 6720? Okay. Now you can do it by hand or on the calculator. You would simply calculate it by first telling the calculator what the total is. So on the home screen you would type in 8. Okay, and then you go to the math menu, go back to probability, same menu that we were at, and then somewhere in there, I don't remember what option it is. 2, there should be an NPR button. You hit that button, or not hit, but lightly press. And then you tell it that you want to pick 5 items out of there, and it will do it for you. Okay, is anyone having trouble using the calculator to calculate this? No? Okay? And then, of course, the most famous example, and then freshmen, you're almost done. In fact, this is the last example, and then freshmen, you'll come up and grab your contests. And then sophomores, I need you for about 3 more minutes. Let's see. Poker. In poker, in a deck of cards, how many total cards are there?
52.
52 cards. Okay, if you're not familiar with the deck of playing cards, you will get familiar between now and the contest, because those are very typical questions that they ask. If you're playing traditional 5-card poker, sometimes they'll ask, how many 5-card hands are there? So what's the number of 5-card hands? Okay, so the question is this going to be a permutation or a combination problem? Well, think about, and again, if you don't play poker, this may not make sense to you, but if you get 5 cards dealt to you, whether you get the ace first or last, does it make a difference in your hand? Absolutely not. So this is an example where the order is unimportant. Order not important, right? So this is a combinations problem. And now that we're comfortable with the notation, we just do what, see what here? 52C5. Traditionally, we say choose for that letter C. So 52 choose 5. You can write it out by hand, but who wants to do that, right? But just in case, 52 factorial, and we divide by the 5 and the difference. That's what the formula says to do. But again, those are really large numbers. You don't want to actually draw them out and cancel. So just type it in the calculator, and you should get something around 2.5 million, if I remember correctly. What is it?
2,598,960.
960?
Yeah.
Thank you. Okay, so lots of different playing hand possible. This is why people that make money in poker are very good at what they do. Okay, freshmen, you are done with what you need to know.
So we are going to room 221. And then sophomores and then juniors, you guys can join us.
Freshmen, come on up, grab a copy of the contest.
And follow me to 221.
Here, you just want to take them?
Sure.
Solutions, contest, there you go. Follow Miss Sobel to 221. Sophomores, you will be joining them in just a minute because there's not much else. Okay, in fact, great. How many sophomores do we have? 1, 2, new sophomore, great, 3. And we're missing Wade, 4. Okay. You probably will not be so much concerned with this stuff. Okay? For you guys, geometric probability is more what you're going to be doing. Okay? And there's really there's not like 4 or 5 examples I can do that will cover everything. Essentially what you have to know is that for geometric probability, the original definition, so the probability of an event occurring, instead of being counting the number of ways that you can get that event, now, since it's a geometric probability, the event will be something about either length, area, or volume. Okay, so what I'll say is the amount, let's say this, favorable length, area, or volume divided by the total length, area, or volume. Okay? And juniors and seniors, you might be likely to see one of these questions on your contest. Okay? We'll do one quick example here. Let's say I have a target. If I had more space, I'd draw a better circle, sorry. Let's say this is worth 50 points. And then out here, anywhere in this ring, you get 30 points. And then anywhere in the outer ring is 10 points. And then let's pretend that the radius of the bullseye is 3 centimeters. And let's say that the radius of the whole target is 10 centimeters. In other words, from here to here is 3. And now if I go all the way to the end, this distance is 10. Okay? What's the probability of getting a bullseye? That's not hard to do, right? How do I find the area of the bullseye would be what? 9 pi. And the total area of the target would be 100 pi. Cancel the pi's. 9 over 100 is the probability of getting a bullseye. This is essentially geometric probability. You're always going to be looking for something about lengths, areas, or volumes. Okay? Sophomores, if you have questions, ask. If not, come up and grab a contest. You will be joining the rest of the team members. And Ms. Sobel's got those contests already. She's got the contests. So just grab your stuff. All right, juniors and seniors. Next topic, mutually exclusive events. All this means is events that cannot occur simultaneously. If that's the case, then we have two things that we need to be able to calculate. And this is a good time if you're a junior or a senior. All this theory that I'm teaching you guys is great, but a lot of times, and you guys probably know from experience, that you can figure things out without knowing all this sometimes. Okay? And a lot of times it comes down to knowing what the word or means and what the word and means. Okay? 90% of the time, if you can split up events with the word or, what are you going to do with all the separate probabilities? Add them. Okay? Somebody remembers. And 90% of the time, if 2, 3, or 4, or however many events that we're interested in can be separated with the word and, you are going to, what? Multiply the probabilities. If you can remember that, and you forget everything else that I've shown you today, you will probably be okay on the contest. Okay? Or means add, and means multiply. Okay? But, let's continue with the theory. If 2 events cannot occur simultaneously, well, I already gave you this one away. You just add the probability of each event. Okay? If they're mutually exclusive, and I'm telling you that it's impossible for A and B to happen at the same time, what's the probability of A and B? Very good. Okay? Now, if not mutually exclusive, then we have the probability of A or B and the probability of A and B. Actually, let's not do that yet. That's going to be a whole different ballgame, but the probability of A or B, you're still going to add each probability. But if they're not mutually exclusive, then there's a chance, well, there's no chance, then it's going to be the case that those 2 events can occur at the same time. Which means that when you're calculating this probability of A, you've probably counted parts of B in there as well. So what do you have to do? You subtract any overlap. And if you're familiar with Venn diagrams, here's essentially what I'm talking about. If you're looking for things to be in A or B, when you count up everything that's in A, you see what I'm doing here? What am I coloring in? Part of B as well, right? And then when you count B, there's one section in here that you counted twice when you counted everything up. Does that make sense? Where is that piece? Right here in the middle. Okay, and that's the probability of A and B. So that's how we subtract. Okay. So here's a quick example that will illustrate. And again, do you need to know all this theory? Well, not exactly. It helps. But some of you can probably figure out these answers without having to think so much about the formulas, as long as you can kind of intuitively see what's going on. For example, let's say in a deck of 52 cards, I want to find the probability if I pick one card, what's the probability of drawing a spade or an ace? Okay, if I'm just going to be a math robot and follow the formulas, you just do probability of spade plus what? Probability of an ace, and then you subtract the probability of a spade and an ace. So, in a deck of cards, how many spades are there? Well, there's 4 suits, right? 4 suits, spades, clubs, diamonds, and hearts. 52 cards. So 13 out of 52. Ace is a rank, meaning that there's one of those in every suit. So how many aces are there? 4 out of 52. And now, how many spades and aces are there? Just 1. Okay, so if you add all these up and subtract the 1, you get an answer of 16 out of 52, which is reduces to 4/13. And here's what I mean about, if you're not going to be a math robot, can you just counted the 16 cards? Probably, right? If you can visualize, okay, well there's 13 spades, and then there's 3 more aces that I haven't counted. Done. 16 out of 52, right? So you can do it that way as well. All right. Conditional probability. Looks something like this. It's finding the probability of an event, let's say B, given A. The notation looks like this. Probability of B, a little vertical line, that means given A. The formula is simply to do the probability of A and B and then you divide by the probability of the whatever it is that you know, which is A. Okay? So a quick example. We don't have to do this. We can do this one here. Let's say we have 20 people in the room right now. Okay? And I want to find the probability, if I pick someone that's wearing a green shirt, that they are female. You can probably just look around the room and count and figure it out really quick, couldn't you? If you span the room right now, let's say there's 20, how many people do you see wearing green?
2.
Stand up if you're wearing
In
green.
a minority.
1.
Yeah, it's just.
Okay, yeah.
You don't count.
Oh, wait, that's great.
No. You're wearing green, right?
But
You're wearing green, stand up. You're wearing green, stand up. So there are 3 people wearing green.
Yeah.
I'm green now.
So just keep track of this.
Sorry.
So what am I looking for? Probability that we pick a female given that they're wearing green. Well, I already know the answer because I see the people that are wearing green as just 3 of them. How many of them are females?
2.
Oh, if we have to think about that, that's kind of
1.
cause for concern. Okay,
1.5.
1.
Yeah.
Okay, so the probability of picking a female given that they're wearing a green shirt is simply 1/3. Okay? Again, yeah, go ahead. Again, illustrating that a lot of times you don't have to know the formulas because sometimes you can just see it. Okay, does that make sense? Now, if we were to use the formula, and let's say there were 21 people in the room, because otherwise my example doesn't make any sense. How many people stood up that were wearing green? 3, right? Out of 21. And now, how many females were there? Oh boy. Well, actually, that's not what I want. What do I need? I need the probability that they're wearing green and the probability that they are female and wearing green, right?
Which is 1 out of 20.
Which is 1 out of 21. Okay? So if you're going to use the formula, it would simply be 121, 1/21 out of 3/21, which also gives you 1/3. Okay? But again, if you don't need to use the formula, you can just kind of see it. That's probably the best way to go. All right. Juniors, you guys are almost done. We just have independent, dependent, and complement, which are pretty easy. Okay. Independent and dependent. A and B are independent. If and only if the probability of B given A is simply the probability of B. This should make sense because if 2 events are independent, that means that one occurrence of one event should not affect the outcome of the other. Right? So if I said, let's flip a coin and let's roll a die, and I said, what's the probability that I roll an even, given that I've already flipped a tail? Well, it's not going to make a difference, is it? Right? Those are 2 separate events. They're independent. Rolling a head, or I'm sorry, flipping a coin and getting heads versus tails will not affect the outcome of rolling a die, and I forgot what I said, but rolling a die and rolling whatever number it is that you want.
Flipping a coin.
What did I say?
Flipping a coin.
Flipping a coin.
Even number on the die.
Even number, okay. So I mean,
Oh, okay. Even number and flipping a coin.
so rolling a die and flipping a coin, these are independent. Neither will affect the outcome of the other. Okay? Now, let's add to this. If A and B are independent, then the probability of A and B, and here's where we're talking about multiplying, is simply the probability of A times the probability of B. So the example I just gave, let's say I want to find the probability of getting an even on a die, and tails on a coin. Those two events are completely independent. I see the word and, which is your cue to multiply, right? So all you do is find the probability of getting an even after you roll a die, and find the probability of getting tails when you flip a coin. What's the answer?
4.
What is it?
1/4.
1/4. Okay, 1/2 times 1/2, right? Okay, last thing, and then the juniors are done.
No, this is.
And that is complements of events. So let's say this bubble represents the entire sample space. So every single outcome is in that circle. And then within that circle, I have a small collection of events that I'm interested in, which we'll call A. Okay? Then that means that everywhere outside of A so everything in blue is what we call the complement of A. Don't. Okay? I do not look like Homer. Okay.
No, I want you to sound like.
I think that was the point. Okay, the notation for the complement of A is A prime. Okay? And now let's see if you guys have been paying attention or at least know something about probability. If I were to add the probability of A plus the probability of not A, what should that, hold on, what should that be? Okay, what is it? 1. Fundamentals of Probability 101. Under no circumstance, if you're on math team, and the question is asking you to find the probability of an event occurring, should you ever put 1.6? It's been done before. Okay? The probability of anything happening is always less than 1. If you add up every single probability in a sample space, you should get 1. Okay? So, from this identity, you get a very useful calculation, which is that maybe you don't want to count everything in A, because there's way too many of them. Maybe you know, however, the number of things that are not in A. So what could you do to calculate it? You do 1 minus the probability of the complement. Okay, so this is a very useful identity. And we'll finish with a little example here, and then the juniors are done. Okay? So let's say I have 6 people, and I want to find the probability that at least 2 of them share the same birth month. So we're looking for the probability that we have at least 2 people with the same birth month. Okay? At least 2 is a very loaded statement because it implies 2 would be a success, or 3. Notice what word I'm using. Or 4, or 5, or all the way up to 6. Hi.
Hi,
She's in 221. So one way to calculate this probability is to find the probability that 2 people share the same birth month, 3 people share the same birth month, and so on, and then add them all up. Well, even 2 people sharing the same birth month is a pain. Because if I have 6 people lined up, I can have person A and B be a couple that share the same birth month, right? Or A and C, you see what I'm saying? A and D. So already, just to calculate this, there's 5 different probabilities you got to look at and find that, and then you have to do that for 3, 4. That's too much. Okay? So maybe we can rewrite this as something like this. The probability of at least 2 can be rewritten as 1 minus the probability of the complement of at least 2. Or think of it as the opposite of at least 2.
Less than 2.
Right. So pretty much, this is the entire sample space. The only event that we're missing is what? Well, one person really can't share a birthday, so it's really just no people sharing a birth month. Does that make sense? So this would be 1 minus the probability of no common birth months. My wife would be yelling at me because that to her means bowel movements, but that's different. She's a nurse, so okay. Anyway, let's finish this. That would be quite a problem. Never mind. Okay. So how do we do that? Well, think of all 6 people being lined up. 1, 2, 3, 4, 5, 6. In order for no one to have the same birth month, if I were to pick person A, and I asked him or her, what month were you born, how many months out of 12 months would be a success so far?
12. 12 months.
12 months out of 12, right? Because that's the first person to go, so there's nothing in common yet. But now if I go on to the second person, and I don't want them to have any matching months, it goes down to 11 out of 12, and so on, all the way down until we're out of people. And if anybody has their calculators out and wants to give us that probability, it is kind of interesting. Anybody got it? What is it? Okay, I'll just do it my way. 12 to the 6th minus 12 times 11 times 10 times 9 times 8 times 7. Come on, help me out. All over 12 to the 6th, whatever that is. Okay, so you get an answer. Moving on. It's not that hard.
Come on.
Everybody's wondering, but no one's willing to do the calculation.
Did you do it wrong?
Well, since 11 times 7 is up to 9. If I knew what I was going to
You
do.
erased it.
Why don't you already have
The probability is 77.72%.
And you did 1 minus, right?
Yeah, I did that already.
So 70, well, let's not do percentage. Point,
0.777. Wow.
pretty high. So 6 people, are just randomly chosen, pretty likely that at least 2 of them are going to have the same birth month. Okay, we could actually try that experiment right now. Out of these 6, what's your birth month?
August. June.
June,
July.
July,
October.
October.
April.
August.
Yay, there it is. Success. August. Or no, yeah. Math in action. Okay. Juniors are done. You may go to 221 and pick up your contest. You probably will not finish because you're probably leaving. So take them home, work on them, and talk to Miss Sobel about what you need to do. Seniors, I'm willing to give you an option here. If you need to go, then you need to go. If you can stay, then let's get it done.
I need someone to record.
Sina needs someone to record.
Oh, I'm taking notes.
That's a competition. I got you. Guys.
Okay.
Sorry, no.
Alright, here you go. Hold it. Hold it.
Bayes' theorem.
Are you gonna go home?
Wait, what probability?
Hold it. Okay.
Look, the chances that Bayes' theorem is going to make an appearance on the contest. Yes. Oh.
Should I start on the page?
Yeah. Oh, it's close.
The probability that Bayes' theorem is going to make an appearance at the contest is very slim. Okay? Out of the
Let's calculate the
contests that I
probability.
have, I've seen Bayes' theorem show up like twice out
Ooh.
of hundreds of questions. Okay?
Let's calculate the probability the Bayes' theorem will occur.
Wait, what did you say?
Good
Oh my
one.
God.
That's a funny guy, you.
So Bayes' theorem is just another way to calculate conditional probability depending on what you know. Okay? You can also calculate it as probability of A times the probability of B given A
This thing.
all over the probability of A times the probability of B given A plus probability of A prime, or the complement of A, times the probability of B given the complement of A.
Is there a proof for this?
Sure, but I'm not going to do it. Look,
So,
you will most likely know when this might be useful. Because you're going to have to be looking for a conditional probability. You see what I'm saying here? And then what else are you going to have to be, what else would you have to know? The other conditional probability. Does that make sense if it's flipped around? That's like the dead giveaway that, oh, I should probably use Bayes' theorem. For example, if I'm looking for the probability that we're going to eat ice cream given that everybody's already left, and I also tell you that the probability that the probability that we're going to leave given that people have eaten ice cream, which doesn't make any more sense. But if that were a problem, it's set up for you to use Bayes' theorem. Does that make sense? Okay? Do you want me to go through an example, or?
No. It's just plugging in.
Let's go on to the next two.
hold on a second. Do you want to erase it?
Question?
I'm
I don't
doing
get
this.
it.
Okay.
Yeah, what's an example question?
I think okay. It would look something like this. It rains, let's say at some city, it rains 5 days out of the year. But the weatherman says that it's going to rain tomorrow. When it rains, the weatherman correctly forecasted it 90% of the time. When it doesn't rain, he incorrectly forecasts rain 10% of the time. What is the probability of rain tomorrow? So, sure.
Isn't it just
So here, let's
90%?
just write down the bullet points. Let's say at some town it rains 5 days out of the year.
Is that our B then?
We'll define it all in a minute. Weatherman says, rain tomorrow. This is according to the weather guy. When it rains, the weatherman correctly forecasted or correctly predicted it 90% of the time. When it doesn't rain, so when no rain, he incorrectly forecasts it or predicts it, when it doesn't rain, he incorrectly predicts that it will rain 10% of the time.
So he correctly predicts 90% of the time?
What's that?
So does that mean he correctly predicts it 90% of the time?
Yes. So I mean, I'm just kind of, so the assumption is that 90% of the time he predicts it correctly, which means then that 10% of the time when he says it's going to rain, it doesn't, and he's incorrect.
Okay.
So he's predicting, hey, it's going to rain tomorrow. 90% of the time he's right, 10% of the time he's wrong.
Oh, that's so wordy.
It is. And then the question is, so we know this, that's the forecast, right? He says, hey, it's going to rain tomorrow. It doesn't rain often, but I know tomorrow it's going to rain. So the question is, what is the probability that it actually will rain? So here's what I did. If you let A be the event that it rains, then A complement is
Not rain.
no rain, right? And let's let B equal the weatherman predicting rain. Why am I doing predicting rain? Because we know the outcome. 90% of the time he's right, 10% of the time when he predicts rain he's wrong. Okay, so that's likely to be one of the events. So what are we looking for here then?
So
Using this notation, we're looking for the probability that it actually
5 over
rains, right?
365
Given that the weatherman predicted that it's going to rain.
So
Does that make sense?
5 over 365
Hold on, let's
times
write it out.
90%.
So, actually, it's already written. I've set it up perfectly. This is what we're going to do, right?
I don't get it, like whether or not the weatherman predicts it right or not, it doesn't change the way if it rains or not. That's it?
Well, no. But the theory is that if he's going to predict the rain, %90 of the time he's right, 10% of the time it's wrong, but there's a lot of other stuff going on.
Is it because like it adds like that clause when it rains? And when
Yes. And it's simply because, so he makes a prediction, so when it rains, that means that he's correct. That's 90% of the time, right? When he makes the prediction that it's going to rain, it doesn't rain 10% of the time. But see, right there, just that sentence, no matter how I word it, that's two events. You see what I'm saying? Rain, prediction. No rain, prediction. So that's two events. Okay? So, I guess we can write it out with words. Essentially, it would be, we're looking for the probability of actually getting rain, and what's the condition or what's the event that I already know has occurred. Yeah, he's already predicted that it's going to rain. So what's the probability that we get actual rain based on the fact that the weatherman made the prediction that it's going to rain? See what I'm saying? So you just kind of follow the formula. You would do probability of rain times the probability of the prediction given that it's rained all over probability of rain times probability that he predicted rain given that it's raining plus, and then we do the complement, the probability of no rain times the probability of no rain given the prediction. And you should be able to plug all these values in there.
So the
Isn't
top
that
one's-
prediction no rain? Not no rain.
Oh, I wrote it backwards. I'm sorry. Thank you.
I hope this doesn't show up.
Okay. So, what's the probability that it rains? It rains 5 days out of the year.
536.
5 out of 365. What's the probability that
90%.
he predicted it correctly?
9 times.
9 times. 90% of the time. All over. And this is just going to slide right underneath, right? Same exact fractions. And now we're going to go ahead and add in the scenario where he's incorrect, right? So, probability that it's not going to rain is
360 over 365.
and now
10%.
yes, 1. It actually kind of makes sense when you put the numbers in there.
Yeah,
But
it kind of does.
11%.
11%?
That is right?
No, it's not that it's right. I got 0.11. So
Yeah, that's what I got.
okay. So what this means then is that what's going on here? A lot of stuff. Okay, hold on. So he is going to predict that it's going to rain tomorrow. Well, even if he says it is, really there's only an 11% chance that it actually is going to rain.
But he correctly predicted
Mind
it.
blown.
Because
right?
it only happens 5 times.
But he correctly
But
predicted
because of the
it.
because of the 5.
Oh, out of those, okay.
Yeah.
Okay.
It's very interesting, isn't it?
So many
You're
things
thinking,
happen,
well, he
yeah.
predicts it right 90% of the time, so shouldn't it be a lot higher? Nope.
Because it doesn't rain that often.
Yeah. That's what throws it off, is the fact that it rarely rains. You know what I mean? Okay. The last two things actually are a little bit easier to follow. I assure you. How much time is left on the recorder?
Okay.
What does it say?
It says, right now it says 57 minutes and 27 seconds.
Okay, so I still got it. Okay. All right, binomial distribution. Have any of you taken AP Stat?
See now?
Of course he's not here. Okay. Okay, binomial distribution is an experiment
I don't remember that.
with a fixed number of trials and each one independent of the other. So each trial is independent. In other words, the outcome of one particular trial is not going to affect all the other trials that are going to be run. Uh-oh. Experiment, fixed number of experiments. We have a fixed number of trials, each one independent of the other. Okay? Only 2 outcomes. Those outcomes I call success and failure. So you're either going to succeed or you're going to fail. Okay, and this is just more notation now. The probability of success is the same for each trial. So there's lots of conditions that need to be met in order to consider a binomial distribution problem. You have to have a whole bunch of repeated trials. Each trial has to be independent of the other one, and the probability of succeeding does not vary from trial to trial. It's always the same. Okay?
Quarter.
Now here's the notation. We'll say X is the number of successes. So that's my definition for the formula I'm going to show you. N will be the number of trials. P will be the probability of success. And Q will be the probability of failure. Okay? So here's what it looks like, and we'll do actually we'll do several. so you can get really comfortable with the formula, and then if you have your calculators, I will show you where to do this. So the probability of x, what does that mean? That means the probability of succeeding a certain amount of times. Does that make sense? Okay. Is going to equal n choose x times the probability of success, and the exponent is simply going to be the number of successes times the probability of failure, and the exponent is simply going to be the number of failures, which you should be able to figure out. If we succeed x times, and a total of n trials, how many times are we going to fail?
N minus 6.
There you go.
Is that it?
So, that's it. That's the formula. Here's how
You live it up for a
problems
second.
typically look. Let's say we flip a coin 10 times. What is the probability of getting exactly 6 heads? Now look, you could do this by hand without this, but then you would have to look, for example, if we have 10 times that we're flipping a coin, you can succeed the first 6 times, right? That's one way to satisfy this. You could succeed the last 6 times. That's another way to satisfy this. Or you can kind of spread those successes out, like succeed the first and second time, and maybe the last 4, or, you know what I mean? There's lots of ways to succeed exactly 6 times. Okay? You can find each one of those out separately and then add them all up, or multiply with the number of ways that you're going to do that. And I mean, this is essentially what it is. This is what that coefficient represents. N choose x represents the number of ways that you can succeed 6 times, or in this case 6 times. Okay, so here's how it would look. How many trials are there? 10. Choose 6. So this coefficient represents in how many ways you're actually going to succeed 6 times. Okay, and then now the probability of success. Well, if we're flipping a coin, what's the probability of success? If we're talking about getting heads, 1/2. What's the probability of failure? 1/2. I'm succeeding how many times? 6. Failing 4 times. So on the calculator, you can do 10 NCR 6 and do 1/2 to the 10th, and you got your answer.
How do you get NCR?
Go to 10. I'll type in 10 first,
Yeah.
and then math over to probability, and then there it is. And then type in 6, and then times 1/2 to the 6th, well, to the 10th if you combine the exponents.
105 over 512.
105 over 512. Beautiful. Okay? Notice you get an exact answer if you actually use the formula, right? If you do, there's shortcuts in the calculator which are called binomial PDF, binomial CDF. Okay? I'm not sure if it'll give you the fraction, but we can find out right now. Okay? For exactly 6, there's a command on the calculator which is binom PDF. I don't remember what it all stands for, but I remember which is which because binomial CDF, C stands for cumulative, meaning that there's more than just one. Okay, and we'll talk about that in a minute. But here's how you program it. Alright, now I haven't done this in years. Does anybody know where that command is? I know what to put in.
Just go to your catalog.
What is it?
You can look in your catalog.
Oh, there you go. Catalog, and it should
It
be one
takes
of the
too
first.
long, though.
It's B something, right?
Yeah, it's a third B.
The third B. So go ahead and hit enter. Okay, and then what you're going to do is you type in 10. So this represents the number of trials. You type in, I believe, the number of the probability of success, which is, in this case, 1/2. And then this last number here represents the what am I missing? I would guess it would have to be the number of successes, right? Let's see if that works. So in this case, we want to succeed 6 times.
It works.
Did we get the same answer?
Yep.
Fraction or no?
No.
So if you try to convert it to a fraction, will it do it?
Yeah.
Okay. Cool. So this is the shortcut. That's the formula. Yes?
You know how to do it on 89? Because I can't find the name.
I will find it. I have an 89. I don't remember off the top of my head, but there's a way to do it.
Oh, I found like what menu it is. It's on.
Oh, what's the actual menu?
It's second bars.
Second bars. Okay.
Second bars.
So that's the shortcut instead of going to second catalog and scrolling down.
Yeah.
Normal PDF, what's that?
Geometric PDF.
There's lots of... I think, actually, does the P stand for Poisson density? No. I don't remember. I haven't taken stat, nor have I taught stat in a long time. Mr. Fu remembers, I'm sure. We can ask him. Okay, so let's do one more example with the same thing. Let's say we flip the coin 10 times. What's the probability of at least 6 heads? So notice the at least, right? Very loaded words there. You cannot do the same shortcut on the calculator because that represents exactly 6. At least 6 means what? What is at least
6, 7, 8, 9, and 10.
Or 7 or 8.
6 or 7 or 8 or 9 or all 10 heads, right? So, let's just write out what it looks like and then we'll talk about what commands to do. So at least 6 means you find the probability of 6, probability of 7, and so on. All the way up to the probability, wow, really? Did I just do ... for skipping 1? Might as well just write them all in. Okay.
So you have to plug it
I
in.
know how to do this. We just did it, right? You would just do 10 choose 6. Probability of success is a half. We want to succeed 6 times. And actually, if you know that they're always 1/2s, what's the exponent going to be for every single 1/2 here? It's going to be 10, because all that's going to happen is succeed 6 times, fail 4 times, well, it's still going to be 10. Okay? What's probability of 7 heads going to look like? 10 choose 7, 1/2 to the 10th, after you combine the exponents, all the way down to 10 choose 10, 1/2 to the 10. Okay, so you can do it that way. It's not horrible, but it's kind of tedious.
It'll take it'll take a minute.
Yeah, it's just going to take some time to actually calculate it. Okay? Now, on the calculator, binom CDF calculates up to a certain number of trials. So the C stands for cumulative. Okay? So if I actually did binom CDF 10 1/2 6, we're telling the calculator to calculate the probability of at most 6. Does that make sense? So at most 6 successes. Okay, so now let's see if we can put it together. If you don't want to type in 5 different calculations,
Shouldn't we
you
do
can
5?
2 commands in the calculator and be done with it. What do I not want?
6, 7, 8, 9, and 10.
No, you don't want 1, 2, 3, 4, 5.
Or 0. 0 also counts. Right? It's possible to get no heads at all. I don't want to include 0, 1, 2, 3, 4, 5. Okay? That can be represented by binom. Which letter? P or C?
C.
CDF of 10 trials, 1/2, and then 5. This will calculate the probability of 0 through 5. That's what that cumulative means. Does that make sense?
Yeah.
So what could I do so that I don't have to do all this? Well, couldn't you just do binom CDF 10 1/2 10? Does that make sense? Because that'll add up all the probabilities for us. and then just subtract out binomial CDF 10, 1 half, 5. Okay? So on the calculator, I would do binomial CDF 10, 1 half, 10. That represents every single probability added up. And if I want 6 through 10, I don't want to include 0 through 5, so I just subtract out binomial CDF 10, 1 half, 5. And you can do this on your own later. Do it both ways. Convince yourselves that this works, and then you'll be good to go. Okay? Thank you for staying. I have one last problem to go through. That's expected value. Okay? And if my calculator does not, or if my computer does not explode when I try to upload this video, we will have a record of me going on and on about probability if you ever want to go back and rehear something explained. Okay?
That's why it's recording.
Alright. Expected value.
So like for math team,
Yes.
in future years we're just gonna watch it.
I don't know yet.
Wait, do you even need me taking notes?
Yes.
Oh, okay.
Because it'd be good to have a written copy of the problems that I do and what I'm going through.
Okay.
So that if someone wasn't here, they can have that and then listen.
Oh.
Thank you.
So at least
I
5
need
pages
notes
worth
then.
of notes.
You have 5 pages?
Yeah. But it's only one-sided,
We
so.
need to
Okay.
take notes. We need to take notes because she's taking notes.
But wouldn't you remember better if you took your own notes than if you just
Yeah.
read someone else's?
I agree.
Write it one more time.
I agree.
remember
Okay.
it.
Expected value. Here's the best way to think about it. I'm a gambling man. Well, not really a gambling man, but I like to pretend I am. The average gain or loss. That's what expected value is. Okay, so essentially if I'm playing a game,
Oh yeah, this one.
I want to know if I play this game once, what's the net loss or gain per play. Okay? So here's a very, and essentially, here's the formula, and I'll explain what this means. You're simply going to add up, that's what the E stands for, expected value. You're going to add up all the outcomes with all their probabilities, and then multiply by the appropriate monetary value. Okay, so typically you'll see it written as, think of the X as amount of money. You know what, let's not do E of X. I don't like that. Let's just do E. So the expected value, okay, can be calculated by simply adding up the products of all the probabilities times their monetary values. So a very quick and easy example to understand is something like this. Let's say we have I guess I switched it from what I used to do. Okay, let's say I'm rolling a die. That's the game. Yay. And it costs $5 to play.
Someone's making.
I don't want to pay $5 to roll a die.
And now, if you roll a 1 or a 2, you win 15 bucks.
Ooh.
If you roll anything other than that, 3 through 6, you lose. So what do you lose? Well, you lose the $5. You don't have to pay any extra. You just don't get any money. Okay? Question?
This is more of a physics question, but
Okay,
wouldn't
let's hold on.
Yeah, he's recording, Christian.
I'm recording.
At a time.
Alright, so there are basically 2 outcomes here. You're either going to win or you're going to lose, right? If you win, you win 15 bucks. Here's the way I do it. How often, that's the probability, how often do you win $15?
1/3 of the time.
A third of the time, right? Because 2 out of 6. And now, how often do you lose?
Wow, 2/3 of the time.
Okay, so there's 2 ways that you can do this.
You lose $5.
So you lose $5.
There's 2 ways that you can do this. Think if you're going to think of just how much money do you get after you roll the die, okay, then at the end you just have to remember to subtract, at the end you just have to remember to subtract the $5. Does that make sense? Okay? You know what? I have a better idea. To avoid confusion.
Can we just do like net gain?
Yes, that's exactly where I was headed. Let's do net gain.
Your brother told me happy birthday.
And shouldn't just be gain, what else could it be?
Loss.
Loss. Let's do it that way. Then we don't have to worry about fudging the numbers at the end.
Wait,
It's his birthday tomorrow. That's how he knows.
Oh, okay.
Okay. So let's recalculate. If you win,
You win $10.
how much money do you actually win or earn?
$10.
$10, because it costs you $5 to actually play. And now, if you lose, which happens 2/3 of the time, you lose $5. Does that make sense? So what's the expected value?
0.
Is it? The
Yeah.
expected value is simply going to be these two added together. So $10 times 1/3 plus -5. Oh wow.
Oh, it is 0.
Perfect game. This is what we call fair.
Is it really?
It is. But you'd have to, obviously you'd have to play a whole bunch of times, right? If you're going to roll it once and be done with it, well, it's not going to be very fair because you're most likely going to lose your $5.
Well,
But if you play a whole bunch of times, let's say 1,000 times, you're going to be expected to come out with nothing. You didn't win, you didn't lose, because in the end it's going to balance out.
yeah, but then again, throughout that time, there will be times where you're up and then you can like
absolutely.
leave while you're
That's
winning.
bound to occur where you go like on some kind of streak where you win, but you know, in the course of
Buy a
1,000,
lottery ticket.
Don't go into my
in the course of 1,000 times,
That's not fair though,
it is going to
unless you buy every
balance out.
single lottery ticket.
Okay. All right. Any questions?
You're old.
All right. Thank you. You can shut that off. Miss Sobel was nice to.
How do you do
give
that?
Some snacks. You guys didn't eat any.
Do you
extra,
press
did
this
you?
button right here, this red one, that says delete?
Would it still be good next week?